have to think about it.
Yeah, right.
Yes.
Or the other way, why don't you just call a BDF strength just BDF plus DH? You just want to make a proposal. I'm just curious, how.
Yes, it's a choice. I think this is a choice, like MH being profiled is also a choice.
Right. Okay.
I think Atlas doesn't let MH to be profiled.
Okay.
You fix it to the measured. I think so.
That I actually have to check that.
Yes.
Okay. Thanks.
Yes.
Since our chair has questions, I probably be allowed to ask too. Don't you do anything in the central region? You don't do any jet veto and jet activity in the middle?
No. Very good point.
Not at all?
No.
Then that's your mistake. You should have done something in the middle.
There is.
If you don't do any separation, how can you separate the current flow with the electric flow?
When we set in this category here, we have a certain number of kinematic variables that we put in an MVA variable. Yes. So a potential variable to add in is this node jet in the region between the two jets. That's what you're saying.
Yeah. Yes? Yeah. That's the best.
This is one variable that is not actually in the PDT. So.
Then of course you have contamination. It's not surprising. That was known in 20 years.
The problem is when you do that, you lose signal. Well, that's what. Yeah.
There's always trade-off. One is the systematics, one is the specifics. You want to purify this to have a lower systematics. Of course, you suffer from specifics.
I think this has been studied and it gives loss of signal. There is a problem of pileup, that you may have some jet that is at high enough PT to reduce your signal if you do the cut.
What did you say about TT bar Higgs? You also said something about glucose fusion. That is from glucose fusion. TT bar Higgs is from glucose fusion to produce this. You didn't say glue to TT bar Higgs. That's the dominant channel.
Right. Maybe I'm wrong. Yes, maybe it's the wrong station. But I'm not sure in the TTH. I'm not sure how they take into account contaminations. I'm not sure how they take into account contaminations. So the glue component, in all of these channels, the glue components in here and in here, they somehow have to be subtracted, yes? So the TTH you have to subtract the glue fusion, the VBF, from the TTH. How do you do that? So you assume standard model. To make it more clear, this analysis here has two jets. Okay? So all these events here have two jets. So in here you will have some of the glue fusion events that have two jets. The same happens for that. Okay? So the way that you predict how many of these you have in here is by using from theory the ratio of inclusive glue fusion to glue fusion plus two jets. That's from theory, standard model. And you take the error into account. It's not measured. And I think that may affect this too. I don't know how much. I'm mostly working in this area. Anyway. Okay, more on this. TTH production. The excess comes mostly from this multi-lepton final state. So since you asked the question, it's very good continuation. So you see how the various final states look like, but in the final states there are many leptons. You can do the analysis in categories of number of leptons. Yes, you see how it looks like. You have W's and Z's, and you require leptons in the final states, and the result is a signal strength of 2 times the standard model, plus minus some big error bar, plus 0.8 minus 0.7, if you can see it. Okay, so this analysis actually gives in CMS the excess. And a little bit more on that here. You see various categories here, and by eye you may not see this excess is significant because there are these error bars. But you can see here, this is not 1, this is 2 times the standard model. You can see here where the data lands. So it's definitely interesting to see both Atlas and CMS seeing excess in this channel. And most of the new data we have will actually help us understand better if there is really an excess or it's just statistical. Or maybe our method is wrong. Okay, another topic that was reported earlier, and I say a few things, is this di-Higgs production. The di-Higgs production, as you heard before, we're not very sensitive at LHC, and even in the super LHC, in the next phase 2, things will be actually difficult, but I think we will reach very close. But right now, we're not that sensitive. However, we can set some limits to anomalous HH production because of physics beyond the standard model. And I think there was a good discussion in the previous talk. The most sensitive channel is the case that the Higgses go to B's. And this is the most sensitive in high mass. And in low mass, this cleaner channel, B gamma gamma, is more sensitive. So these are the observed limits and the expected limits that we set here in terms of cross-section, as a function of a mass of something heavy x in this channel here. So imagine something x here with some mass, and these are the limits we can set. Okay. Let's move to SUSY. Okay, the SUSY results are keeping updated as we get more and more data, and you see here the gluino production. We set limits in the mass of the gluino up to 1.6, 1.7 TeV by using the strong gluino production. In this case, the gluinos go to quarks and neutralino. So there are many searches, and I have to show, I can only show a few slides. There are R-parity conserving, R-parity violating, gauge-mediated SUSY breaking, and the highest cross-sections come for things that have gluino and squark pairs with decays to jets and missing ET. These are the best things you can look at and set limits. I know this is a complicated plot, but I try to put some explanation of what it shows. It shows gluino production. You can see here the channels, gluino production to top, bottom, and light quarks through PP goes to gluinos and gluinos decay to these quarks. You see here. And these are the limits we set. All the analysis, if you want more information, are in these papers. And they are using different final states or different method observables to do this. I have here the graph to help you, to guide you how this channel should look like. And there is S-quark production that I show here. So you go directly, if you can see, I'm not sure if you can see, you go directly to S-quarks, and these guys decay to quarks. Here is the top again, here is the bottom, here is the light quarks. Okay, and you can see the limits that we can set with this analysis. And now they are all 13 TeV, as you see, which is great. Another thing you can do, since the strong production limits are saturating, then you can use electroweak SUSY production shown here to set some limits or to see something. So you see here again the same diagram I showed before, but now you have these diagrams here. You're going to neutralinos and you have S leptons. You can assume the masses of these to be degenerate, and you can set the limits here. So you can exclude gluino with a strong process to 1.25 TeV, and the LSP to be less than 750 GeV. The electroweak excludes chargino up to 1 TeV. Okay, so this is the main result. Here we have the zoom. Here we have the zoom of this plot on the right side, so you look better how the limits look like, and the various papers and the various final states, if you want to look more into that. And in one slide, due to lack of time, you probably have seen this before because this was shown in ICHEP, and we will be updating that. The BSM, beyond the standard model exotic limits are 13 and 8 TeV here. Whenever we have 13 TeV analysis is shown here. So you can see that we are in the multi-TeV mass range for various models and things that we set limits for, like excited fairness, compositeness, large extra dimensions. And both Atlas and CMS have plots like that, and there is nothing really seen yet. So we set these limits. Like in the last talk again, the dijet resonances is some standard thing we do from the day one, basically, looking for excesses. And you see here these typical results. And you see these are some models that have resonances as an example to see how the peak should look like. Of course, as you heard before, no surprises here, but the new physics may still be there hiding under this background, that is large background. One thing to say is that we set cuts here in the opening eta angle between the jets to avoid more background coming from T-channel QCD dijet production. Something maybe people don't pay attention when you think about this. And these are some limits, some observed limits we set in various models. Again, the usual models you saw before. And there are here shown how the limits are obtained for students is that you get your model, which is these lines, and you get the observation is this line versus resonance mass. Where they meet is where you set the limit for students who haven't done this before. This is standard software to do this that has been developed over the years after a lot of effort to do that. So it's not so simple, but it's what we use at LHC. And dileptons, very clean signatures that also may couple to new physics beyond the standard model. Again, also CMS doesn't see excesses, and there are certain limits that are being set. Also here we have very high, because of statistics, we have the probability to see some very high PT invariant mass event, and you see here some examples in the dimuon around 2 TeV and the dielectron. Okay, for completion I have to talk about taus. Now taus are also leptons, so dilepton resonances in the tau channel. Search has been done. It's interesting, tau is very difficult. It's not as clean as the leptons. It's more difficult than the leptons like muons and electrons. So in general they are not competitive, but they're a very interesting object. And we also check in various categories, various final states for excesses. And we set also limits. You can see here different final states, tau to electron to muon and to hadrons. Right, I'm towards the end of my talk, and the 13 TeV, for people who remember last January we have a whole workshop here about the diphotonic cells, and we scrutinized the details of the data in both years, in run 1 and run 2 back then, what we had. And my opinion was that it was premature, to say it in a very elegant way back then. It was premature because of this picture. So what you see here, actually what you see now here is 13 and 8 TeV versus the mass. X is diphoton invariant mass. Okay, you see here the p-value. Okay, you see here the p-value, and if you focus in the, I cannot even see very well, but if you focus in the 750 region, which is here, if you zoom in, you see that the red is the 8 TeV. It has more than 2 sigma significance, and it's amazing because the same happened for Atlas back then. But the blue, which is the 13 TeV, and actually the 13 TeV has 16 femtobands of data now. The 13 TeV doesn't see anything, basically. But you should also take into account something we discussed last January, that if you look in the various categories, because people use categories in the gamma-gamma analysis, like barrel, end cap, etc., you see all these spikes from both experiments. So you have to take into account the look elsewhere effect from for both experiments, that you may actually have a spike in the same mass. Yeah. So this can happen. I think it looks like this is what happened. In 2015 versus 2016, that's also interesting. CMS went back and reanalyzed the, sorry, this is 2015 and 2016. So we put back the 2015 and 2016 data, and you can see here how the excess looks like. Okay, so in 2015 with the 3 inverse Feldelmans, we also have a similar more than 2 sigma excess, actually close to 3 sigma. I wanted to say that here we analyze the ATTV data, so sorry I'm confused. Okay, so the bottom line is that the excess is not there. And we will see with more data, but it looks like it's not there. Dark matter. So that's also interesting because I'm very happy to see people yesterday and the day before actually referring to data and using the data to test their models. So it's rather interesting in this group. So dark matter searches are done basically looking for events. You trigger on events that you have a jet, but then you may have very high missing ET because on the other side you see nothing. But this is maybe due to something exotic that is dark matter related. So we set limits to mediators and we set limits to the actual dark matter particle mass, for example, neutralino, and you can see here the limits. Okay, in blue is the mediator, and the red, or whatever this color is the neutralino. Okay, and you can see here various papers, and you can see here the final states that these things were looked at. So we are touching the 1 TeV mass in terms of mediator, and we are somewhat lower for, quite lower for about factor of 2 roughly with a mass of the LSP. Okay. So more on that. Actually, you can see here what we call monojet and monogamma. So we're looking for events that have 1 jet or 1 gamma, and this is the missing ET. And here is the missing ET, and you can see, for example, here how some models predict an excess over expectation. I don't know if you can see these points. Is the red line here? One example. You see the excess, how it should look like. Data consistent with expectation, we don't see excess. So one way to present this, an interesting way to present this, is to put it in this familiar plot as limits on the spin-independent cross-section of the dark matter versus the mass of the dark matter. Okay, and you see the usual experiments of direct detection here. The limits, of course, are not very competitive in this particular analysis, but that's how they look like. Actually, the invisible decay of the Higgs is more interesting in terms of that plot. It looks like it's more sensitive. So also I saw people using this data in their analysis yesterday. For example, yes, we saw some presentations yesterday that used this 0.2 or 20% branching ratio limit that data show. So basically these are Higgs production here, that the Higgs decays to invisible particles, for example, dark matter. You need a jet somewhere. You need jet or jet somewhere, so you can have something to trigger on. So you trigger on these jets, and then you look for missing ET, events with missing ET, and you can use that to constrain decays to invisible particles. Okay, and the limits we set in Atlas are very similar to CMS, by the way, is 24% branching ratio to invisible. Okay, I think Atlas is 23%, so it's about the same, which is very interesting. So that will improve with more data. We translate this to 90%. confidence levels limits in this usual plot, and you see now here for scalar dark matter and fermion dark matter, it looks quite more sensitive than the previous slide. Okay, here the assumption is less than 20%. The decay branching ratio of Higgs to invisible, which is close to that, just below.
Do you know which one is the most sensitive of these three channels? I think the associative production is the most sensitive, but I'm not sure.
You think that?
The last one.
The VH?
Yeah. But for analysis anyway.
So in Atlas, the BPF channel is most sensitive.
The BPF?
Yeah.
Because of you can separate, you can take the delta eta.
That's right. Yeah.
What is the trigger? How high you need to go with the PT for a single monojet? The first one. You have to go extremely high for this.
The trigger.
What is the trigger requirement for the monojet? It must be very high. 100, 170, 100, 150?
I don't know if there is a special trigger for that. Is there
For
a special
the
trigger?
monojet in Atlas, we trigger the vicinity. So 150 G.
Yeah, I don't think there is a special trigger for the PT of the jet, high PT. It's missing it. Okay, so we presented new results from CMS. I should say that we expect now at least 35 femtobarns of 13 TeV data. I think the number should be between 36 and 37 because I was looking how much data are actually now going for the physics groups. I should say that we can talk offline about if we see something or not, but I should say that we're blind. We're blind, meaning that we're doing the analysis on simulation, and I think that's fair. We're doing the analysis on simulation, and we're not looking at the data yet before having blessing from the performance groups. I think similar thing happens with Atlas, but maybe Atlas is faster. Yes, because we have calibration issues. So after the data is calibrated and reproduced, etc., and we get approval, only then we can unblind. We have decided on the cuts and everything. So actually now people wouldn't know much if you ask them offline if you see something, if we see something. Maybe Atlas is more ahead of us, so ahead of CMS. Okay, so I apologize because I didn't cover everything. There are other interesting things that could be covered, but you can find the results here. And there are new results coming out as time goes by, so you don't have to wait for February. There are new analyses becoming public all the time, so if you go there, you can actually see if a new analysis is coming out and check it out. Okay, thank you very much for listening.
Sorry to ask about some particular model, but can you say something about the right-handed gauge boson and also the two Higgs models?
To say something?
Yes, so bound or something.
I don't know. The answer is I don't know. I don't know if.
You looked for W prime and Z prime as well?
The answer is I don't remember, or I don't know. So you want?
Maybe heavy gauge boson.
If it's not here.
Okay. Maybe it's not here.
Maybe gauge bosons there.
Yellow ones.
The yellow box.
Genetically assuming that.
Oh, W prime and Z prime. Oh, it's okay for the moment.
Yes, heavy gauge bonds. What was your question about Higgs? What did you say?
No, whether there is some bound, upper bound for the W prime and Z prime mass, or two Higgs, and also two Higgs models.
Two Higgs models. Two Higgs doublet model.
Yeah, so charged Higgs, for example.
Yes, of course. Yes, there are bounds, and the two Higgs doublet model we have used Higgs for lepton. We have used Higgs for lepton to set bounds. Sorry, I don't present. I haven't presented it here. But there are bounds. Yes.
So the chart Higgs, if chart Higgs is below the top of decay, then the bond is extremely strong, and the branch refraction is less than 1% already. But if the chart Higgs above top of decay, it's very weak.
Okay, thank you.
Any other questions or comments? So I figure people are eager for the coffee break. So let's thank our speaker for this morning, and we can chat more offline.
Very good. Probably got more copies for some reason. I have no idea why. Very good.